All right, stationary points. Exercise 10C and D. Essentially, you go through how to find a stationary point and then identify the types of stationary points. Stationary points, by definition, again, let's see if you remember from last year. What is a stationary point? Can I please have? Let's go with Charlie. What's a stationary point? When the gradient equals 0, which we find as delta y delta x, which means the rate of change is going to be 0. So the gradient of a tangent line at one particular point is going to be 0, and it's indicated by the dotted lines at A, B, and C, as we can see here. But they aren't all the same type. So just because you've got a derivative at 0 doesn't mean that they are the same types. Does anyone remember what the 3 types of stationary points were? Give me one. Let's go with Krish. What's one type of stationary point? You have a minimum, which is this one over here. So it reaches the bottom, so minimum. What's the next one? Phoenix. What's the other two? We've got a maximum. Very good. We've got a maximum type. And then the last one, what is that, Simon? Inflection. Very good. Now, usually we call it local maximum and local minimum, just because it's localized here. You could have a graph with multiple stationary points. So hence, when you say maximum, it's sort of implying that it's the maximum value. So we say local maximum in terms of stationary points, which the next exercise you'll find that we then look at maximum value, or they call it absolute maximum and absolute minimum. All right, so we now know there are 3 types to identify, and the 3 types you can identify by using, and if they do ask this in your SACs or exams, and they ask you to justify, then one of the only ways for method students, we usually use a gradient table. Okay, so when you justify, you need to actually show that the gradients at a particular, from the left of a certain point and to the right of a certain point, the value has to be given. What you can't do is something like this. You can't just write, because you already know it's a local maximum, most times you already know it's a maximum, and let's say you know it's at x equals to 1, hypothetically, right? You can't then just say, I pick, say 0, x equals 0, and then x equals 2, so say x equals 0, x equals 2, and I'll just write positive, negative, because you haven't proven, you haven't justified to me that the gradient is truly positive. You probably know it is a maximum, but you haven't justified it for me. So it means that at this point, when you say positive, you got to actually sub in the value into your derivative and tell me what is the value. Once you tell me what the value is, then you can say, yes, it's positive. It looks like this. It's a positive gradient. So you need a value. It needs to be something like positive 2. Sub it in, solve. This one you already figured out. That's your stationary point. And this one you have to sub in and solve to then get a negative value to then say, yes, therefore it's justified. So those justified questions usually is about 3 marks or so. You do need to show some steps. Yeah, so that's what I was sort of saying. So method students, we use a sign diagram. I believe special students can use double derivatives if you're in an exam. Not sure about SACs. I think then it's a discussion between the teachers whether that's going to be acceptable or not. And if we wanted to, we would be more specific. We'd say something like justify with a sign diagram. Then that would be more specific that even if you know the double derivative, you can't use the double derivative. But for now, I would say yes, you can. You can use a double derivative because most method students are also special students, at least at the exam level. So they will accept double derivatives, and therefore our SACs, we should. But if we wanted you to use the gradient table, we would tell you. Okay. So that's one thing to keep in mind when you're justifying stationary points, to make sure that you give the actual value. All right. So beyond the fact that a stationary point is delta y delta x equals 0, let's do a problem solving. So let's go and look at exercise 10C, question 7. Let's see how we're going to do this. So we've got a curve with an equation y equals ax plus b over 2x minus 1. So we've got 2 parameters, a and b, which we don't know, but we do know it has a stationary point at 2, 7, which means delta y delta x must equal to 0 at this point. A, find the values of A and B, and then B, the coordinates of your other stationary point. Ooh. All right, I'm going to pause the video just for a second here and see if you can even find the values of A and B to start off with. Okay, so it should be as straightforward. This is a typical exam 1 type question where they give you an equation and they say that there's a stationary point, and then from there you're meant to be able to find 2 equations to solve for A and B. I'll give you guys 3 minutes. Let's go. See if you can use your chapter 9 skills, derive. Let's see if you guys got the second part. B. So we know that A is 2 because I gave it to you, and B equals 9. So even if you didn't get the first part, the second part, resubstituting it in, the derivative, I just replaced A and B. We know that the stationary points occur when derivative is 0, so I let it equal 0, and then from here it's just solving for x. So I move the 2 across, I swap the denominator and the value on the left side, or you can do a bit of manipulation there. And you end up with negative 18 on negative 2, gives you 9. Get rid of the square, so you square root, that's where you get your 2 possible solutions. And then you solve for x from there, add 1 on both sides, divide both sides by 2, you should get 2 or negative 1. You already know there's a 2, so the other one must be negative 1. So back in to find the y value, and you should end up with negative 5. Can you get a show of hands who got negative 1, negative 5? For those that did it? Cool. All right, excellent. So that is just a taste of what it's like working on stationary points. That's a typical exam 1 style question. It's good to practice this kind of understanding using the 1 point. Find 2 equations. So one is substituting into the original, and then one is substituting in the derivative. So I find that's your typical exam 1 skill. The next 2, feel free to have a go. This is now a bit of analysis. So if you have a look at the next one, that's exercise 10D, question 15. X squared times e to the x. They're just saying find the domain for which the derivative is going to be less than 0, meaning it's going to be a negative gradient, is what you're looking for. Obviously, it's a lot easier if you have a CAS calculator. Type it up and sketch it. But if you didn't, how would you do that in a SAC as an example? So first thing to identify, this would be a product rule because it's x squared times e to the x. Use product rule, find the derivative. So you get f dash x equation, and then I want you to analyze that. So hopefully that's the skill to take out for the SAC version. For the exam, this would be pretty easy if you just type it up and you analyze where it is. But if you didn't have a CAS, how would you solve for the domain such that the derivative is going to be less than 0? So that's a hint there. Use product rule, find the derivative, and then analyze it from there. The second part's quite similar as well. So 10D question 14. I think previously in one of my notes, I had a similar equation, and I was giving you some guidance on how to predict what the graph looks like. If you don't have a CAS, and this was in exam 1, the ability is to use limits. Try to think of what happens when the number gets infinitely large, infinitely small, and then infinitely close to 0. When you do that, you should be able to visualize what this graph kind of looks like. Or at least if you think about exponentials with a negative power, what would you expect it to look like? So that's something worthwhile to check out, see if you're playing with analyses, because it's a lot easier if you just chuck it in a CAS. But what I want you to train is the ability to look at an unfamiliar equation and then predict what it looks like. That's the key analysis skill that I can't truly teach, but you have to kind of learn to unwrap yourself. Okay, and that's where 10C, 10D is nice as you're practicing it. The more you do, the more you put yourself in that uncomfortable position to try to figure out what the graph will look like and look at limits. That's the best way to learn how to analyze. Okay, so I'll stop there and I'll write up the solutions as you guys are doing this, or you can practice again. In order to do these, you have to be pretty good at chapter 9. If you're still in chapter 9, work on chapter 9. All your product rules, quotient rules, chain rule, derivatives should be smooth. And analyzing derivative graphs before you do chapter 10. Chapter 10 relies on the fact that those are strong already. Okay. All right, I'm going to stop the video or more pause it and then I'll show the solutions afterwards. Is it for today then? So that's the key things to take out. Theory-wise was to learn stationary points. This is problem solving. And then the next two is analyses. But pause the video to check for any of my solutions to see if it makes sense. Otherwise, that's your